Okay, so in the previous class, we began the second order system by classifying two underdamped system having a pair of complex conjugate poles, and the critically damped system by having two real repeated poles, and also overdamped system that has two distinct poles. And we said that is the generally speaking for the say RLC circuit or massive spring damper or two tangle water in series. And if you go to the unity feedback block diagram in MATLAB coding, you have to use the closed loop transfer function. When it comes to the Simulink, you have to use what? The open loop transfer function G that we found from here. Remember, I'm just recapping what I have done in the previous class. And this G, if you find it, is going to be omega n square in S square plus 2 zeta omega n. And here is y, here is x. Unity feedback, assuming that the sensor is ideal. Here is E, error signal. So you see that the open loop transfer function for the second order system, or G, is omega n square divided by S square plus 2 zeta omega ns. But you can write this. I'm just showing that, not teaching you yet. I'm just showing you. You can factor out one s. You're going to have s plus 2 zeta omega n. Open loop transfer function means that in the feed forward path, this path, feed forward path, you have 1 over s. I taught you. What is 1 over s? As a controller, I taught you. What is 1 over s?
Set.
No, controller. PID. Which part of this is 1 over s? Remember? You're having a notes. 1 over s is, remember, Laplace of integrator. Yeah, go ahead. What? It is, no, integrator. Yes, integrator. Okay, integrator. So the second order system in this format has one integrator already. And just I'm telling you, I'm not teaching you yet. Integrator function in design a controller, maybe I taught you, is to remove a steady state error signal. The function of is that. Plus rejecting disturbance if you have. So it says this second order system in this format already has an I controller. On the other hand, you can replot this as, or making more clear, x. When it comes to Simulink, you can do like this. See, because these are the same. 1 over s plus 2 zeta omega n. They are multiplying to each other, that's right? It's going to give you the same here. So you see, you can regard this as on the y. As you see, you have integrator already here, I controller. And I'm going to show you shortly by mathematics that this I affecting to remove the steady state error signal when your input is impulse and step. Can I go to the next page? Everybody? Yes? So now look at the case of the first order system. We had actually five inputs. 1 impulse, 2 step, parabolic, and ramp. Finally, frequency response means sine and cosine. And at the end, I'm going to plot the Bode diagram of the second order systems. Okay. So let's go to this, and I'm going to tell you that, guys, I'm gonna apply when the zeta is smaller than 1. Means that you have two poles, a pair of complex conjugate poles, minus zeta omega in previous class, plus I omega d. Remember, I taught you this. If you go to the complex plane under the system, so you have this, a pair of complex conjugate poles. Here is omega d, for God's sake, and here is zeta omega. So if that's the case, you see that the x of s, this is x of t, is impulse. X of s now you know is 1 in frequency domain. So your y gonna be omega n square s square plus 2 zeta omega ns plus omega n square. See from here, I just copied. X is 1. But you have two poles. Obviously, you can write as this omega n square in s minus s plus p1 in s plus p2. Right? Because I defined p as this. Poles. I have to change the signs here, guys. Minus p1 minus p2. Here we go. Right? Minus p1 minus p2. Two poles. That's right. You know from high school how to do this. Right, everybody? So now we have to find, you're going to say this is A over S minus P1 plus B S minus P2. Right, now you have to find it. And maybe A, this is a trivial method, but I don't want to go to residual that maybe you don't know it, few of you. This is SP2, this is SP1, sorry guys. I'm developing with you. Okay, so as we did previously for the first order system, you have to sort for A plus B in S minus A P2 minus A P1 is equal to natural frequency square plus 0S. We don't have S here. Saying that, you get A plus B is 0. So A is equal to minus B. And this is equal to how much? Natural frequency squared. So you get, where I said this is B. P1. Sorry guys. So being said, you say minus A P2 minus B P1 is equal to omega n square, but the A is equal to minus B I'm putting here. So you're gonna have B P2 minus P1 is equal to natural frequency square. So we have P1 and P2. P2 minus P1 gonna be minus zeta omega n. So suppose P1 is plus and P2 is minus. Minus I omega d minus plus zeta omega n minus I omega d is equal to omega n squared. This with this goes to hell. So you get B gonna be minus omega n squared to I omega d. There we go. I'm writing here, say P1 is minus zeta omega n plus I omega d, and the P2 is minus zeta omega and minus I omega d when you put in here. So when you have that, you have A. A is omega n square 2I omega d. So if you put here, can I go to next page? Yes. So you get y of s is equal to omega n square in 2I omega d. And here is 1 over s minus p1 minus s minus p2. I just put here. You got it, everybody? So now we're going to go to find time domain Laplace inverse. Being said, y of t gonna be omega n square 2I omega d, and you know that Laplace of, guys, I taught you having those e minus at plus is 1 over s plus minus a. See what I'm saying? So because here's minus, you're gonna be plus. So you're gonna have e p1 t minus e p2 t. Here we go. So what is p1? We have it here and p2. So if you replace here omega n square 2I omega d e minus zeta omega n plus I omega d in t minus e minus zeta omega n minus I omega d in t. We can factor out, for God's sake, from high school, we can factor out this e minus zeta omega n t from both sides. So you're going to have e minus zeta omega n t omega n square 2I omega d e plus I omega dt e minus I omega dt. You don't have to know the process. I'm teaching you because I'm professor. I have to teach you how you're going to see this Simulink and MATLAB. Okay. But the Euler, remember, Euler says I theta, I taught you several times, is cosine theta plus minus I sine theta. This is Euler we are using. So let me call this as parameter A to avoid writing multiple times. I'm saying this is A. So it's going to be A cosine omega dt plus I sine omega dt for the first term, and again cosine omega dt minus in minus, because here's going to be minus, plus I sine omega dt. Bye-bye to New York. So I'm writing everything now. Omega n square e minus zeta omega nt divided by I omega d multiplied by 2 I sine omega dt. This I with this I goes to Denver. This 2 with this 2 goes to LA. So y of t, when you have underdamped system and your input is impulse, gonna be sorry guys, and you know that omega d I defined to you is omega n 1 minus zeta square, previous class. If you put here and with one of these goes away, okay, gonna be omega n 1 minus zeta square. Sorry guys, still this COVID hurting me. Zeta omega nt sine omega dt. Bingo. Here we go. Okay guys, I want to plot it first here and then in MATLAB and Simulink. I told you, what is the name of this term? E minus zeta omega nt. What's the name of that? Minus zeta omega nt. Decaying term, that's right. It goes to 0 when t goes to infinity, and this is parabolic. So, can I go to next page? Everybody?
Yeah.
Good. So if I want to plot it, shortly I'm going to show in Simulink. Y, t. Input to the system was impulse, unknown. Here we go, impulse, huge force. Based on what we derived, we have to know this, not the rest. It says the output gonna be transient harmonic sine omega d damped frequency being vanished by this decaying term. So it's gonna be like this. Here. And finally, output follows input. Means what is 0? What is 0? The steady state error signal is 0. When input is impulse. For what? For this underdamped system. You see this harmonic, but it's vanishing. But the proof from finite value theory is here. ESS is the limit of S input to the system 1 plus open loop transfer function I taught you when it goes to 0. A limit of S, x of S is 1 because it's impulse. And the open loop transfer function is S squared plus 2 zeta omega n S. Whatever is here is 0. 0. Bingo. 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 You got it, everybody? Yes? Huh? Good. I'm gonna stick to this graph because I'm gonna add to it. Because I wanna try critically damped system and overdamped system with the input of the impulse. Then I don't want to repeat myself for the step or ramp. I just want to plot it for you. Okay? But only I'm going to do this for this because the rest is going to be the same like this. Okay? So case B. If your system is critically damped, as I told you, you have two repeated poles minus zeta omega n. Two repeated real poles, not pair of complex conjugate poles. Where is that? I want to show it to you. Oh, here we go. Two repeated poles here on each other. Two. These are critical, as I told in the, and you know that this left-hand side, remember, is stable. Okay. If that the case is, again, y is equal to gonna be omega n over s plus s minus p1. S minus P1 square. These are the same. P1 and P2, they are the same from high school. Now I want to go to the time domain. Laplace inverse. But I have to use a trick. What's the trick? I taught you the ramp Laplace is 1 over s squared. Good, I see the square here. Also, I taught you that E minus SA in f of t gonna be, you have in your notes, is S plus A. And here, if this is plus, here gonna be minus. So Laplace of A SA t gonna be, because this is already here, 1 over S minus A square. We got it, everyone? I taught you previously, you have your notes. So we see that exactly here. So the inverse Laplace of this, for God's sake, y of t gonna be omega n square t, and your A is P1, E P1t. Simple like that, we derive together. But I have to replace P1 here. So let me change the color. So y of t for the impulse input, but for what? For critically damped system is omega nt, omega n square, E, your P1 is zeta omega n, minus zeta omega nt multiplied by t. Okay, guys, don't write. All of you look at here. Stop writing now, because I want that to take your attention to some point. For underdamped system, your solution was exponential and harmonic. That promised you that you're gonna have harmonic vanishing. Do you see any harmonic term here? Yes or no? Huh? Do you see any harmonic term here? No. So don't be angry. So so you're gonna have this. There we go. No harmonic. No sign. No oscillation. Means no oscillation. No vanishing oscillation. So this is for when I say critical damp, means slower and what? And no oscillation. This is for underdamped. Zeta is slower than 1. As you see, again, steady state error signal is 0 for that. Nothing changes. This is 1, this is the same G. That's right, so it's 0. Now let's go and consider the overdamped system. Here we go, overdamped system. In the overdamped system, as I taught you in the previous class, that you are on the stable region, you have two distinct real poles. And I'm going to show you with this color. Here we go. Two distinct real poles. Right? So can I go to the next page? Everybody? So when the is this, so you get P1 as you have in your notes, so I'm just repeating, minus zeta omega n plus omega n 1 minus zeta square, or I'm sorry, this is zeta square minus 1, because zeta is smaller, greater than zeta square minus 1, and the P2 is minus zeta omega n minus omega n zeta square minus 1 for overdamped system. Again, so you have y of s is omega n square. Again, here s minus p1, two distinct real poles, p2. Okay, so you know that you have to again find it. A over S minus P1, I'm repeating myself, but as the underdamped system P2, you're gonna be A S minus P2 plus B S minus P1 S minus P1 in S minus P2, and you know that changing the color again, I'm writing the same A plus B in S minus A P2 minus B P1 is omega n square. Again, A is equal to minus B, nothing changes, so you're gonna have B P2 minus P1 is omega n square. Just putting there P1, P2 minus P1 minus zeta omega n minus omega n. I'm just dropping I in the underdam, get I plus zeta omega n minus omega n. Zeta square minus 1 is equal to omega n square. This goes, you get B as minus omega n square divided by omega n 2, obviously, these two. Zeta square minus 1, one of these with these goes to where? San Francisco. Angle B is omega n 2 zeta square minus 1. From here you get A is minus of that. Omega n 2 zeta square minus 1. Bingo. Bingo. Just implement here together. So y of s gonna be omega n 2 zeta square minus 1. Again, s minus p1 minus s minus p2. Time domain, for God's sake. Laplace inverse. Can I go to the next page? Yes, everybody? Huh? Can I? Good. So you get, oh my god. Don't tell me that you deleted that. Oh, okay. Okay. So you get, as I did, y of t is omega n 2 zeta square minus 1 e p1t e p2t, and replacing p1 and p2 two poles, you get y of t for the overdamped system with the input of impulse is e minus zeta omega n plus omega n zeta square minus 1 t minus zeta omega n minus omega n zeta square minus 1 t. And these are numbers, real numbers. But when it goes to 0, these are all goes to 0, but much slower. Okay, as I promised you. I'm gonna show you simulink. So if I want to plot it, let me change the color to black. I'm gonna have this. This is slower. And obviously no oscillation. See? There is no oscillation term, just decaying terms. So the black one is for overdamped system. Again, nothing changes. Input is impulse. It's the same order system. Error state goes, steady state error signal goes to 0. You got it, everybody? Now you know this. I want to say, okay, 2. I don't drive mathematics. I'm just going to show you the results. Steady state error signals. I say now x of t is unit step. So x of s gonna be 1 over s. So y gonna be omega n square divided by s in s minus p1 in s minus p2. Here your s comes here. I remember this when I was undergraduate. So when I say if zeta is smaller than 1, means underdamped system, a pair of complex conjugate poles. If I'm not wrong, after you do the operations, answer gonna be this: 1 minus e minus zeta omega nt cosine omega dt plus zeta 1 minus zeta square sine omega dt. Here we go. Let me fix this. Here we go. Unit step. I'm just plotting everything here for you, because after that I don't want to drive. I just want to drive the final, plot the final answers. Y t. What was the name of this, guys? I told you just now. What's the name of this term? E minus zeta omega nt. Huh? Decaying term means goes to 0 eventually. You see harmonic force, but damped harmonic force. So if this is your input, unit step, it says that after a while, all this term goes to 0, and your output, it follows your input, output goes by 1, but with some vanishing harmonic terms. Here we go. You're gonna see this. And exactly this is your car suspension system, guys. This is your car suspension system after passing a bump or a step on the road. It's gonna oscillate a little and then goes to new elevation. You got it? This blue line is for underdamped system. If you go to the overdamped system, I don't want to drive it. I just want to show you, because based on what I taught you in the impulse, you see that for the overdamped system and critically damped system, there is no oscillation. But what? But what is slower? So for overdamped system, we're gonna have this. Here we go. This is for for critically damped system is this. And for the overdamped system, again, we don't have oscillation. Let me choose this guy. But much slower. Here we go. And this is for overdamped system. In all of them, output follows input. Means what is 0? You tell me. What is 0? Error signal. Steady state error signal is 0. You got it, everybody? Yes? Let me try with the final value theorem. Can I go to next page? Yes. So final value theorem says ESS is limit of, as I taught you, S input to the system, 1 plus G, 1S goes to 0. your your input is step 1 over s this time. 1 plus omega n square s in s plus 2 zeta omega n. Guys, I taught you this from my mind. Please look at your book if this is right. Actually, this is right, but for double checking, okay? So, when s goes to 0, this s with this s goes to that, gonna be limit of 1. Here you have s. Any number divided by s is infinity. Infinity. 1 over infinity, 0. Bingo. And it doesn't change anything if your system is under damped, critically not over damped, because input is the same, system is the same. For any cases that I showed in the plot, steady state error signal. Let me change the color of this because I don't want to confuse you with the critically damped system. Okay, there we go. Steady state error signal goes to 0. I'm gonna talk about this area and this area later after I teach you the error signals. Okay, after I teach you the whole error signals. Case number 3. When the step input to the system is ramp, you want to increase the temperature of the room from 0 to, I don't know, 75. You want to increase the speed of your car from 0 to linearly, I mean, to 60 mile per hour ramp input. And you want that the output, which is your car, follows the input. So by saying this, I taught you the Laplace of this x of s is 1 over s squared. So your y, I'm not driving again, I'm just plotting here, just wasting your time. Gonna be s squared now, this time s minus p1, s minus p2. So I'm gonna plot everything here. This time. Y, t. And this is your input, x, ramp. If your system is under damped, I'm gonna prove this mathematically, okay? This is gonna be your, when I say under damped means you're gonna have oscillation. Look at here, guys, oscillation, and here, parallel to this. This is for under damped system. What do you see here, guys? You tell me. What do you see here? Output follows input? Does the output follows the input? Come on. No. Yes. Yes. Let's go to the final value theory. Limit of s x of s. X of s here is 1 over s squared. 1 plus g. G is the same. Omega n squared open loop transfer function. S plus 2 zeta omega n. One of the s with one of these goes to hell. So what you have here, if you write, is gonna be a limit of, if you take down s, okay, gonna be s plus, and this s with this goes to the New York. So you get omega n squared s plus 2 zeta omega n. Everybody agree? I just take down this s to this denominator. You got it, everybody? When s goes to 0, this goes to 0. Oh, what happened? This s goes to 0. Oh. This s also goes to 0. So what you have here is 1 over omega n squared over 2 zeta omega n. This omega with one of goes to some Bernardino, and the result is 2 zeta. Oh, you have steady state constant value. Constant steady state error signal. Here we go. Here we go. Which is function of damping ratio and natural frequency. So if I change my system to critically damp or over damp, this never vanishes because input is the same, ramp, system is the same. So now I'm gonna plot it for you. So, but you know that for critically over damp, there is no oscillation, this transient oscillation. So it's gonna be like this. Here we go, no oscillation. I'm gonna sell this as critically damped system, and you know that this is a little slower. This is over damped system. But all they have a constant steady state error signal, and you have to fix it. Now, guys, listen to me. Don't write. All of you, listen to me. Don't write. At the page 1, where is page 1? I told you that the open loop transfer function G has one integrator, 1 over S. And I said integrator that I'm going to teach you later is to remove steady state error signal. You see that until your input is a step, which is 1 over S, right? Impulse, which is smaller than that, for what is that? Come on, for the step, which is one integrator. So steady state error signal is 0. But when I increase is 1 over S squared, you see that the open loop transfer function integrator cannot fix it. So it means that you need another integrator to remove this steady state error signal. You need another integrator. I'm not teaching you, I'm just showing you. Okay, I'm going to teach you later after the midterm. Okay, so and the final case for when x of t is parabolic, means x of s is 1 over s cubed. Guys, for ramp we had a steady state error signal. We are increasing 1 over s, so you expect to see huge error signal. Okay, so you see y gonna be omega n squared again. Here now s cubed, s minus p1, s minus p2. I'm not driving, I don't want to waste your time. I'm just plotting. Y. This is your input, parabolic from high school. So for zeta smaller than 1, before going there, let me calculate the steady state error signal. S x of s. X of s is parabolic. 1 over s cubed. 1 plus g omega n squared. S in s plus 2 zeta omega n. When s goes to 0. This s with one of the goes to hell. So you got limit of s squared plus omega n squared s in s plus 2 zeta omega n when s goes to 0. 0, 0. 1 divided by 0, 1 divided by 0, infinity. Means that your error signal is increasing with time. So when you have this, because under them you have oscillation, and then this increases. See, error signal increasing with time. Okay, this value. So this is for under them system. When it doesn't change, so zeta is critically down. It doesn't change. Again, gonna be infinity because the input is the same, system is the same. So, but you have no oscillation, transient oscillation. So you're gonna be this. Okay, this is straight line length. Okay, and when overdamped, no oscillation, is smaller, slower response. Let me change the color. Here we go. Okay, but again, error signal increasing. The zeta is smaller than 1. And this is zeta 1. You got it, everybody? Now, like the case of the first order system, I want to make a table. But now I'm going to make a huge table. Actually, a short table. Here we go. You saw that. Impulse, unit step, ramp, parabolic. And this is the first order system. 1 over tau s plus 1, closed transfer function. And second order system, omega n squared in s squared plus 2 zeta omega ns plus omega n squared. You have your notes for here steady state error signal. We are talking about error signal. Here was 0, 0, tau, time constant, and infinity. Here we have 0, 0, 2 zeta over natural frequency, and infinity. You got it? So it means you as control engineer, after this point, you need controller to fix this. Because you don't need controller here for the steady state. After here, you need controller. You need controller for these inputs. On the other hand, X, sorry guys, X, you need a C to G, first order, second order, third order, 10th order, I don't care. G can be any order. Okay, I'm gonna go there eventually, don't worry. X and Y. After this point, with these inputs, you need this to design, to fix that, to fix these error signals. You got it, everybody? Yes? Now, knowing this, let me take you back to the, we don't have time for the simulating, hopefully next week, next class. Imaginary real part. majority of the dynamical system, they would love to have a pair of complex conjugate poles. Like your car. Like your car. Suspension system. Robotic is a specific class of problems. We need the critically down system because we don't want to have the transient oscillation. Airplane. You're on the airplane up there, a turbulence coming, hitting the airplane. So you don't like, when you're on an airplane, suppose you can say a huge turbulence comes as a step function, continuous step function. You don't want to have experienced this. Okay, you don't want to experience this slow. You always experience this in the airplane, I bet. You experience this. This is a pair of complex conjugate poles. So I told you if you connect this to here, to the origin, here was omega d, here was zeta omega n. This angle that we name as phi, from trigonometry you can say cosine phi is zeta omega n over omega d. But I define to you that the omega d is omega n 1 minus zeta squared. Bingo, bingo. So this angle, sometimes you need to calculate that. It's cosine inverse or cosine of zeta over 1 minus zeta. This is only a function of damping ratio. Only function of damping ratio. And this radius r can be used, can be calculated as what? As high school. Square plus omega d square. Omega d is omega n square 1 minus zeta square. This with this goes away, so that radius is gonna be natural frequency. Here we go. This is natural frequency of the system. You got it? Now, if you keep natural frequency of the system constant, and change the damping ratio, you're gonna have eventually a circle here. You're gonna have a circle here. Okay? We got it. These are the problems I wanted to teach you. But your car suspension system, your airplane, this suspended ejection system, too many things, as I told you, they would love to have underdamped profile. When you have an underdamped profile, why I'm teaching you this? Because this helps you to design controller eventually. Okay? We have many parameters. One of the parameters that I taught in the vibration was this is control class. What's the name of this? Overshoot, or maximum peak in percentage for underdamped system, because underdamped system has such vanishing profile, oscillating vanishing profile. Another parameter that next class we have to work on after simulating is these two. The response settles down. We get TS1, TS2, settling time in 2% criteria, 5% criteria. We're gonna calculate these. Okay, Why? Because it's gonna give us a sense of where we have to locate this by controller. These complex conjugate poles. Okay? Settling time. So I'm gonna stop it here. Next class I'm gonna first make the Simulink file of the second order system, and then we're gonna continue from here by calculating the overshoot, how to design the complex conjugate poles based on the overshoot and settling time of the system. Okay? Then I'm going to talk about the dominant poles, and then I'm going to go to defining K, P, KB, KA, static position error signal, static velocity error signal, static acceleration error signal, and then we continue, hopefully, process stability criteria. After that, we're going to have midterm. Okay? I'm sorry, after this, after the Simulink, you have to go to the body plot of frequency responsibility, and then those. And after those stability criteria, we're going to have midterm. After midterm, we're going to go to PID controller, root locus, and lead lag controller. Okay? Any questions, guys?
Okay. Thank you.
Thank you. Let me stop it.